All right, in this lesson, you guys are going to start on the next part, the next chapter that we're going to work on, which is about random variables. So today we're going to focus on what are called discrete random variables. The learning goal is that you will understand how to compute probabilities of discrete and continuous random variables. But today we're just going to focus on the discrete part of that. So, when we looked in the last chapter at probability models, remember that they describe the possible outcomes of a chance process and the likelihood that each of those chance outcomes will occur. So if we use the simple example of tossing a coin 3 times, then the sample space is either all 3 heads, 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 tails, tails, heads, heads, tails, heads, 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 tails, 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 heads, heads. Okay, I can't even say. But anyway, there are 8 equally likely outcomes. So the probability of each of the outcomes would be 1/8. However, if I wanted to look at how many heads occurred, then our model changes a little bit. So what we're going to do is define a variable, which we're going to call x, as the number of heads that will occur. And what we want to ask ourselves is how likely is each possible value of x? So let's look at the different possibilities. The first possibility says x is 0. In other words, we had all 3 tails. The next possibility is that x is 1. If x is 1, that means we have only 1 head and 2 tails. Right? So we could have heads, tails, 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 heads, tails, or tails, tails, heads. If x is 2, then we have 2 heads and 1 tail. So heads, heads, tails, heads, tails, heads, or tails, heads, heads. Or finally, the last possibility is that we could have all 3 heads. So now what we're going to do is look at the probability distribution. This is like the probability model of that random variable which we're defining as x. It's random because we don't know what its value is going to take on in the short term, but we can predict what values it takes on in the long term. So here in the top row, we're looking at what values x can take on, 0, 1, 2, or 3. And then in the second row, we're looking at the probability of each of those values. 1/8 for 0, 3/8 because there were 3 outcomes that had 1 head out of the 8 total outcomes. Also 3/8 for 2 heads because there were 2 outcomes that had 2 heads. And then again 1/8 for a value of 3. And here's a graph of this distribution. You'll notice that it looks an awful lot like a histogram, right? The only difference here is because my random variable is discrete, which means it only takes on specific values. It doesn't go, it's not continuous. It can't take on any value between 0 and 1. It can only take on the value of 0 or the value of 1 or the value of 2 and nothing in between. So instead of having bins like we have in the past with a histogram, we have just like the number down here, the value of the random variable. 1, 2, 3, and those are in the center of my bars. And then of course on the y-axis we have the probability of each of those values. But for all intents and purposes it behaves just like a histogram does, and we're going to look at its shape like we look at the shape of a histogram. Okay, so there's a graph of that same probability distribution. So what if we want to do some calculations with this probability model or this probability distribution? For example, what's the probability that we get at least 1 head in the 3 tosses of the coin? Basically what we're asking here is the probability that x takes on the value of greater than or equal to 1. What's the probability that x is greater than or equal to 1? So one way we could compute that is to add the probabilities. The probability that we get 1 head plus the probability of 2 heads plus the probability of 3 heads would be 3/8 plus 3/8 plus 1/8, or 7/8. That wasn't too bad because in this particular case we didn't have too many different values that x could take on. But the other way that we could do it is to use the complement rule. So the probability that x is greater than or equal to 1 is 1 minus the opposite of that, the probability that x is less than 1. But if x is strictly less than 1, the only value it could be would be 0. So that's the same as saying the probability, 1 minus the probability of x less than 1 is the same as saying the probability, 1 minus the probability of x equaling 0. So that's 1 minus 1/8, and just like before, we still get 7/8. Okay, so a random variable and a probability distribution. A random variable takes numerical values that describe the outcomes of some kind of chance process. And basically all we're doing here is what we did in the very last chapter with our probability models and looking at the sample space and the probabilities of each value in the sample space. We're defining that, all of those outcomes, as a random variable. The only thing is they have to be numerical values or quantitative. I can't say what's the probability of being red and define x as being the random variable red. I can only define x as random variable that takes on quantitative values. Then the probability distribution of a random variable gives the possible values and their outcomes, just like our probability model did in chapter 5. So a discrete random variable x takes on a fixed number of outcomes. That means it doesn't go on forever. It can only take on a certain countable number of outcomes. And each value of x has to have a probability between 0 and 1. And of course, the sum of all the probabilities has to add up to 1. So what I want you to do now is pause the video and watch the first example in the links, the first example on APGAR scores. I do want you to include this example in your notes, so if you need to pause or rewind or whatever to do that, make sure you do. But pause this video here, click back to the wiki, and open up the first example video on APGAR scores.